So, hi folks. This is the second of the tele-seminars for this semester, and our speaker this time is Professor Syed Jafar from the University of California at Irvine. He's been working on several areas on physical layer communication, information theory kind of stuff, and he's been extremely successful at it, receiving several awards, including like the NFF Career Award and our Young Investigator Award. And in fact, he is kind of the first person to kind of think about interference alignment. I guess he's going to tell us all about that. So I will hand over to Syed. Thank you very much.
Thank you. Of course, it's my first video teleconference presentation as well. So let me know if something stops working in the middle or if I need to speak clearly, or I guess I could improve the quality of the voice if I just pick up the phone and hold it next to my mouth. But for now, I will just use the speaker, and if it doesn't work, then tell me. All right, so the title here is From Cellular Networks to Index Coding, Interference Alignment Perspective. So speaking of interference alignment, the idea, of course, has been around for at least, well, 6 years now, and quite a lot has happened on this topic. So as far as giving talks on related issues, it's actually got harder to present talks on interference alignment because there's always a bunch of topics to pick from. So even for this presentation, I cannot talk about everything, of course, but I will talk about some of these topics that you see here. And again, these are also too many topics. I will probably just touch upon them. The things I will talk about in more detail are index coding and cellular blind interference alignment, those two topics. All right, so network capacity is something we recognize as the holy grail of network information theory. It has guaranteed job security for information theorists for quite a while, and it's supposed to be like that for any time in the future as well. So of course, this problem is an open problem. The capacity region is not known. But let's think for a second that what if this problem could be solved? What if you could solve or find the capacity region of an arbitrary network? So here is an example, and the details are not important here. Just consider a simple network. In fact, it's been greatly simplified. We've made all possible assumptions that would allow us to solve this problem. It's a three-user interference channel, a deterministic channel, in fact. And with all those assumptions, of course, we're able to solve it. But what does the solution mean here? So that's the solution, or in fact, it's 1/6 of the solution, because you have to take these inequalities, and you also have to take all permutations of the indices 1, 2, and 3, and then you would get more sets of inequalities and everything put together. Then, of course, you have to optimize over the distributions of V1, V2, V3. So that's what a solution would look like. The point of this slide is that for these network capacity problems, because there are so many parameters, so many transmitters and receivers that you have to worry about at the same time, even if the solution could be found in the most general sense, it may not be very useful because it is just extremely cumbersome. So let's try to be a little less ambitious. Instead of going for the full capacity region of these discrete memoryless channel models, how about if we talk about a subset of these networks, which is linear communication networks. So these are networks where the output, which I'll call the Y vector, the output is just a linear transformation of the input. The inputs are X, and that linear transformation is the matrix H. So of course, why do we care about, why is this an interesting class of networks to think about? Well, it turns out many communication networks that we do work with generally are essentially linear communication networks. So for example, wireless networks, the output is a linear transformation of the inputs, and of course there's noise, and I'll say something about that in just a minute. You can also think about network coding problems, for example, on wired networks. Again, if the coding operations inside the network are linear, then the end-to-end transformation from the inputs to the outputs, you could think of that again as a linear transformation. So it would again be a linear network. So it would be nice if we could have a theory of linear communication networks where we understand what their capacity limits are. So let's take a look, consider this in a little bit more detail. So in a wireless network, especially if it's a one-hop wireless network, then these linear transformations or the channel weight would be chosen randomly by nature. These are things that you would not be able to control. Whereas in a network coding problem, for example, these linear transformations would be polynomials in linear coding coefficients. So whatever coding operations you perform inside the network determine what this H matrix is. So you have some control there. Now in the wireless setting, we're dealing with complex alphabet and complex numbers are closed. So it has nice properties. Every polynomial will have solutions. So it has many nice properties. We would like to work with complex numbers. On the other hand, if you're talking about network coding these linear problems, then you may be working over finite fields, like a GFQ. And it has some disadvantages because whereas on the one hand, complex alphabet is richer and generic, has this property of being closed, finite fields do not enjoy many of those properties, and sometimes the solution may depend on the choice of the field. That would be an unfortunate outcome, because if we want to understand something very fundamental about linear communication networks, we would like somehow that understanding to be based on the topology of the network rather than the choice of the finite field. Okay, so we would like to work with complex alphabet, but what's the problem? Why cannot we just directly go ahead and assume everything is complex? Well, over complex alphabet, if you don't involve noise or power constraints, then the problem would become degenerate because the capacity would be infinity, right? Because you have infinite resolution. So as a necessary evil, you do have to involve noise and power constraints just to make the problem not degenerate. But on the flip side of it, when you involve noise, now it takes away from the fundamental linear network, because now noise is adding in addition to the linear interaction between the signals. So what that does is it makes the network noisy, and so the capacity results you get will be approximate or not exact capacity because you're only addressing the linear aspect of the problem. Whereas in network coding or deterministic networks, there is a chance that you may actually get the exact capacity, and we'll see that often you will. So that's now, of course, the two models are very similar. In both cases, essentially, we're looking at a linear communication network, y equals hx. So you would expect there to be natural relationships between them. And indeed, they do have natural relationships. So for example, in the wireless network setting, if you think of a unit link, just a point-to-point Gaussian noise link, what is its capacity? Its capacity is approximately log SNR. So as I said, with noise, we have to deal with approximations. It's log SNR. Whereas in a network coding setting, if you have a noiseless link that carries Q array alphabet from some finite field Q, GFQ, the capacity would be log of Q. So you can think of log SNR as being equivalent to log of Q. So if you want to express capacity in a way that removes as many parameters as possible and leaves only the topology of the network, well, then you would like to normalize the capacity. So in the wireless setting, for example, you would like to express capacity as normalized by the capacity of a single link, the capacity divided by log SNR. In the network coding setting, you would again normalize by the capacity of a unit link. So you would divide capacity by log of Q. So these are normalized capacities. And you can go further and say, well, even now, even though I do normalize by log SNR, my capacity may still depend on SNR. So if I also want to get rid of the dependence on SNR, so the only thing that's left is just the topology of the network, and that would be the large alphabet limit. That is, you say, even in network coding results, very often you will use this argument that if the field size was large enough, then this will work. The same thing you're doing in wireless networks as well. You're saying, well, if the alphabet size was large enough, that is the degree, if the SNR was high enough, then in the high SNR limit, this normalized capacity is what we call the degrees of freedom. So as we will see, in these normalized notations, the capacity of the index coding problem and the degrees of freedom of the wireless network will turn out to be the same. Not always, but most of the time. So in most examples, we'll see, you will find that these two are the same quantity because they're both essentially solving the underlying linear communication network. Okay, so now what is interference alignment? Let me say a few things about that. As a simple description, an interference alignment in a linear communication network is the following. So In a linear communication network, you have a receiver. Because the communication network is linear, the receiver will see linear combinations of all the transmitted symbols. Okay, so it has a bunch of linear equations containing the variables being the information symbols being transmitted by the various transmitters. So typically, when do you need interference alignment? You need it when the number of equations is much smaller than the number of variables. You cannot really solve for all the variables, but you would like to solve for some of the variables which you're interested in, and the rest of the variables you don't care about. So what is it that will allow you to solve a system of linear equations for some of the variables that you're interested in, even though the number of equations is much smaller than the total number of variables? That property is interference alignment, and what it says is that the undesired variables have to occupy a smaller space. That is, they have to align into a smaller number of dimensions. So in this talk, as I said, I will try as much as possible to use network coding examples. So I will also motivate interference alignment with a network coding example. So here what you're seeing is a 3 unicast example. You have 3 sources, S1, S2, S3 on the left, and the 3 destinations on the right. Note that they're a little bit staggered. So source 1, that is a yellow source, wants to talk to destination 1, which is not directly across from it, but a little bit down here. So it's a multiple unicast setting, meaning that there are 3 messages, one from source 1 to destination 1, another message, independent message from source 2 to destination 2, and so on from source 2 to destination 3. So let's see what we can do in this network. Well, first thing you want to see is what you can do with routing. So in this case, it's easy to see that routing capacity is only 2. And again, when I'm mentioning capacity, it's always in a normalized capacity, meaning assume all these links have the same capacity, which is if you're operating over GFQ, it's log Q, as I said before. So the basic unit of capacity is the 1 link capacity. So in those units, the routing capacity here is 2. Why is it 2? Because you can see easily, if I remove 2 links in this network, the link at the very top and the link at the very bottom. So if I remove these 2, now you notice that all sources are disconnected from their desired destinations. No source has a path to its desired destination anymore. So all the desired information in a routing solution will have to flow through those 2 links that I removed. So therefore, the routing capacity cannot be more than 2. That's just a sparsity bound. What if you use random linear coding? So what if these nodes which can perform linear coding, they just chose some random linear combinations? In that case, again, you can see that the capacity cannot be more than 2. And why is that? Well, look at any destination. Well, I hope you can see the pointer. So destination 3, for example, they will see 2 random linear combinations, or 2 equations, because it has 2 paths arriving at D3. So each destination sees 2 equations, and if those equations happen to be some generic linear combinations, then you can at most solve for 2 variables from 2 equations. So therefore, the capacity of a random linear coding cannot be more than 2. But what is the capacity of this network? So when I say capacity, notice I'm not talking about just linear capacity. You can do whatever you want, linear, nonlinear operations, arbitrary kind of complexity. But the solution will turn out to be very simple, and the solution is the capacity is 3, and it requires interference alignment. So let's see how it works. So in this solution, each source will send 1 symbol. So let's say source 1 will send the symbol X, source 2 will send the symbol Y, and source 3 will send the symbol Z to their corresponding destinations. So source 1 is sending out X. What do these nodes do? Well, there's no network coding to be performed here because there's only 1 incoming edge. You just forward what you get. So you just send X along over here. What does this node at the bottom do? Now this node can do network coding because it has multiple edges coming in and only 1 edge going out here. So in this case, I chose this to be the sum of X and Y and Z. It can be any linear combination. It doesn't matter. It's X plus Y plus Z, and at this point you can think of it as random linear coding. How about this link at the top? Well, again, choose a linear combination, just a different linear combination. So the important thing is don't use the same linear combination that you had here. It's a different one. So far, no alignment has happened. Now, what will this link do? Well, again, this link's choices, it really has no choice. It will just send whatever it received on all of these 3 links. That's the best it can do. It will send 2X plus 3Y plus 4Z on each of these 3 links. Now, let's go to these links, these nodes. this is where the network coding that happens will involve interference alignment. So now is where interference alignment comes in. So what does this node do? Well, it will stand for x plus 3y plus 4z. You can see that it can obtain this linear combination. Well, what is that? Just 4 times this minus y would give that 4x plus 3y plus 4z. And why is that a good linear combination to send? So let's look at destination 1. Destination 1 wants to decode x. Remember, it wants to decode the symbol x. So y and z are interference. So there are 3 variables, but it has only 2 equations. So what you want, or what should happen, is that the interference has to align. So let's see if things align here. By alignment, what I mean is, for destination 1, these are the 2 linear combinations it sees, or these are the 2 linear equations it sees. If you notice, I can think of these 2 linear equations, even though they involve 3 variables, I can think of them as involving only 2 variables, because 3y plus 4z you can think of as 1 variable. So what has happened is 2 interfering variables have aligned into 1 interfering variable, or in other words, 2 interfering dimensions have aligned into 1 dimension. So now, of course, you have 2 equations, 2 variables, and you can solve for x. In this case, you would just subtract 1 equation from the other. You would have 2x from where you can get the value of x. So something similar will happen at each of the destinations. So for example, go to destination 2. This node will forward the linear combination x plus y plus 2z, which is again an interference alignment situation. Why? Because destination 2 wants the symbol y, so x and z must align. So again, if you note, these are the 2 equations available to destination 2, and x and z are aligned. Why? Because you can think of x plus 2z as 1 variable. So this would be just twice that variable. Okay, and you can find y from there. Similarly, of course, at this node, you will generate the linear combination 2x plus 3y plus 3z. Destination 3 wants z, so x and y must align. And indeed, they do align. So again, 2 interfering variables align into 1 dimension. That allows you to solve for z. So that's what the point of this slide is. This is what interference alignment is. That when you have fewer equations and the number of variables, and you still want to solve for some of the variables. Of course, you cannot solve for all the variables because you don't have enough equations. But if you want to solve for some of them, then the remaining variables, the undesired variables, have to align into a smaller space. Okay. Now, if we think about this problem again, what's happening here, if you look at the sources and destinations, everything in between as a network, then it is a linear network because we are performing linear operations. But the alignment was achieved by optimizing that network itself. So the network coding operations that we performed were inside the network. So in a way, we optimized H itself. We made this transformation nice so that alignment happened. But in many settings, for example, if we were using random linear coding, or if these channels were generated by nature, for example, in a wireless network, then you would have no control over H. So the question here is, what if H was randomly generated? Could you still achieve the same interference alignment advantages? So in this example, we will look at random channels. This is a wireless network, but you could think of it as a network coding problem with a random linear network coding inside the network. It makes no difference. If you think of it as a wireless network, you will get the degrees of freedom. If you think of it as a network coding problem, you will get the exact capacity. They will turn out to be the same number, 4 over 3 in this case. The DOF equals 4 over 3. So what is this problem? This is an X channel, or you can think of it as all unicast. What that means is there is an independent message for each transmitter-receiver pair. So there's a message from transmitter 1 to receiver A that we call A1. There's a message from transmitter 1 to receiver 2 that we call B1, and so on. So there's 4 messages here. These are independent messages. So as it turns out, I'm just telling you the answer here, that this network has 4 over 3 degrees of freedom. And what that means is you should be able to send all these 4 symbols, A1, B1, A2, and B2, over 3 channel uses. Okay. So let's see how you would do that. And again, the point here is to explain how interference alignment works. So look at receiver A. So this is a linear network. So the receiver will see some linear combinations of the transmitted symbols. So over 3 channel uses, remember our goal is to send the 4 symbols over 3 channel uses. So over 3 channel uses, it will see some 3 linear equations. So let's say I just randomly wrote these equations, didn't think about it. So if you look at it carefully, you will find that from these three equations, you cannot solve for A1, A2, which is what receiver A wants to do, because there's nothing clever about these equations. Okay, so, but what can we do to make things better here? As I said, we cannot control the channel. Right? The channel is not decided by us, so we cannot try to make the channel different. But what controls do we have? So if you think about what the transmitters are doing, let's look at transmitter 1. Over the 3-channel uses, it can send different linear combinations of A1 and B1, because A1 and B1 are the two symbols it wants to send. Now the choice that it has is what specific linear combinations to send. That is what it can control. It cannot control the channel, but it can control which linear combinations it's going to send. That's called pre-coding, by the way. So this is the pre-coding operation that will allow us to achieve alignment. So assume that, for this example, that these are nice choices. These are good choices of linear combinations to send from the transmitter. Then what would happen at the receiver? Something nice would happen, and what would something nice look like? It would look like this. So why is this a nice set of equations? It's nice because interference is aligned. Let me make it explicit. I've rewritten the same 3 equations again, but this time you can see that, remember, this is receiver A. So he wants A1 and A2, and for him, B1 and B2 are undesired variables. As you can see in these 3 equations, B1 minus B2, or B1 and B2 have aligned in the sense that B1 minus B2 can be thought of as one variable. So essentially, you have 3 equations in 3 variables. The receiver will be able to solve for A1, A2, and B1 minus B2, although it will never be able to say what B1 is or what B2 is, but it will be able to solve for the aligned variable. So now I will rewrite the same set of equations in a vector notation just to get used to how we talk about these things. So the 3 equations we will write as shown here. So what we'll say is that A1, the symbol A1, is received along the signal dimension. This vector represents the signal dimension, -2, 1, 2. So that's the direction along which you're receiving the symbol A1. Similarly, the symbol A2 is being received along this direction, and B1 is being received along this vector, and B2 along this vector. Okay. And what is alignment? Alignment means that the undesired symbols, that is B1 and B2, the spaces, the signal spaces that they occupy, so B1 is this vector and B2 is this vector, they span a smaller space than if they were independent. So here, these 2 vectors actually span only a 1-dimensional space because they're parallel, which means that interference occupies only 1 dimension, or you can think of it as there's only 1 interference variable, B1 minus B2. They're all equivalent ways of saying the same thing. So using the same vector notation, we can also go to the transmitter, and here we could say that what the transmitter is doing is sending the symbol A1 along the direction 3, 1, 2, which are the 3 coefficients it used over the 3-channel uses, and is sending the symbol B1 along the direction 2, 1, 4. Those are called beamforming vectors or pre-coding vectors, and that's what you have to optimize to achieve alignment. So in a short, more compact notation, we will say that the transmitter has a choice of the beamforming vector, and along that vector, he can send the symbols. He can choose 2 vectors along which to send the 2 symbols. Similarly, we didn't, to keep things from getting too cumbersome, I didn't go into the detail of transmitter 2, but transmitter 2 is also doing the same thing. It's choosing 2 vectors along which to send the 2 symbols A2 and B2. What does the receiver see? Well, the receiver sees everything transmitted by transmitter 1 and linearly transformed by the channel. Whatever channel exists between transmitter 1 and receiver A, that channel will transform whatever was sent by transmitter 1. And then, of course, whatever by transmitter 2 will be transformed by the corresponding channel, and the receiver will see a superposition of everything. So that's what is being seen by receiver 1. And similarly, of course, receiver 2 is seeing a linear combination of the transmitted symbols as well. So what would you like? I mean, how would you frame the interference alignment problem here? The problem would be that you're given H. You have no control over these channel coefficients. H is given. What you can choose are the pre-coding vectors, the V's. And what you would like to happen is that at receiver A, the undesired vectors, that is the vectors carrying the undesired symbols, which would be HA1, BB1, which carries B1, for example. These are the undesired vectors. They should span only 1 dimension. Same thing at receiver B. So how easy is it to solve that kind of problem? Well, in this case, it's very easy. The X channel happens to be one of the easiest cases. For example, I mean, there are many solutions. One simple solution could be that you could choose any vector. In this case, we chose the vector 1, 1, 1, and we would make all the undesired vectors equal to 1, 1. That would be one way of achieving alignment. So in the next slide here, I will just show you explicitly what that solution looks like. So it is, again, the same problem we had before. It's 2 transmitters, 1 and 2, 2 receivers, A and B, 4 messages. It's the X channel. And we will look at this channel over 3 channel uses. So this blue graph represents the first channel use. Orange one is the second one, and then this gray one is the third channel use. But in this figure, I have them all shown at once. But remember, this represents 3 channel uses. So let's see, transmitter 1 wants to send the symbol A1 to receiver A. So what should it do? What beamforming vector should it use? Well, so as it turns out, what it will do is it will look at the interfering channel. That is, if A1 needs to go to receiver A, then the interfering channel would be the channel to receiver B. And it would just invert that channel. So if this channel was H1, H2, H3, A1 would be 1 over H1, 1 over H2, 1 over H3. That's the beamforming vector for A1. Similarly, transmitter 2 has to send A2. It needs to go to receiver A, but it will base the beamforming vector on the channel to the undesired receiver, that is receiver B. Let's say this channel is H4, H5, H6. You invert that. Similarly, you can continue. Let me say this. So what did we accomplish by inverting these channels? So now if you look at the undesired symbols at receiver B, A1 and A2 are undesired. If you just see what happened here, because of the inversion of these channels, A1 and A2 both appear along the same vector 1, 1, 1, which is what we said. We could make the line vector 1, 1, 1. You can do the same thing with B1 and B2 as well. So B1 is undesired at receiver A, so you could just invert that channel. B2 is also undesired at receiver A, so you could invert the corresponding channel, choose that as the beamforming vector, and that would align B1 and B2 at receiver A. Of course, now you have to write everything because the desired symbols are also reaching their receivers, but you will see that they're not aligned. It's just a simple matter of checking that these things work out. Okay, so these desired symbols are in a space that's linearly independent. So in fact, you can solve these 3 equations to find your desired symbols. And that's interference alignment in this simple setting. Of course, notice that the transmitters need to know the channel coefficients. It's very important here because the pre-coding vectors are pretty much very strongly dependent on the channel coefficients. So you do need. That was a simple example of interference alignment. Let's go to a more complicated, in fact, let's go to the most general scheme that we have so far. And so I'll present this scheme, and then I will show that the scheme pretty much solves every interference alignment problem where you have the channel knowledge at the transmitters. Okay, so that's the assumption here, that you do know the channels. So what is this scheme? Well, let's consider a K-user interference channel. On the left, you have the transmitters. On the right-hand side, you have these receivers. Each transmitter has an independent message for its corresponding receiver. And of course, because this is a wireless channel, they will all interfere with each other. So how should we, what's the best to do in this linear communication network? You can think of it as a wireless channel. You can also think of, as I said before, you can think of it as a network coding problem if you want. In that case, you will find the exact capacity. All right. So the scheme is based on basically two statements is all you need here. The first one is there exists, and I will show you in the next slide how to construct such a space. But for now, I will just say that there exists a way to construct a signal space V that will be invariant to all undesired channels. That's the first statement. The second statement is all transmitters will use the same space V. Okay, so now let's see what that means. So consider receiver 1. Okay, so now as we said, all transmitters are using the same space V. So transmitter 2 is using the space V. Now transmitter 2 is heard by receiver 1 through a linear transformation. Let's call it T1. So what does receiver 1 hear? It hears T1 times V. But as we said, since T1 is an undesired channel, and the V space has been designed to be invariant to all undesired channels, so therefore T1V will turn out to be essentially the same as V. And we will see that later, but for now, just that's all we need. T1V is the same as V. Similarly, transmitter 3 is using the space V. It goes through a transformation T2V. So receiver hears T2V, but because this is an undesired channel, T2V is also guaranteed to be the same as V. So it's just V, and of course the span of V and V is the same as span of V. So you just write it one time. You can do that at every transmitter. Every transmitter, every undesired transmitter is sending the same space V and reaching the receiver and aligning in that same space V as well. So all these alignments have to happen. So V has to be such a space that satisfies these conditions. Now, what about the desired transmitter? Transmitter 1 is also using V. Now, there's a channel between transmitter 1 and receiver 1, which is H11. But the important thing here is that V has not been designed to be invariant to H11. It has only been designed to be invariant to undesired channels. So H11V will turn out to be a different space from V, because the desired signal will be separable from the interference. And the same thing will happen at all the other receivers as well. So if you go to receiver 2, these are all, the red channels are all undesired channels. So the V's will, so V is supposed to satisfy this property that all undesired channels, it remains invariant. You will just get V. And from the desired channel, you will get H22V, which again will be different from V. Same thing will happen at all receivers. Okay, so that's the picture, that's what the picture looks like at the end. So if you want to know what's the degrees of freedom per user, it would be the number of desired signal dimensions, which is H times V, for example, H11 times V, divided by the total number of signal dimensions. That is the signal dimensions occupied by interference, which is the size of V, plus the dimensions occupied by desired signal. Now, because H is an invertible channel, it's in fact here it's just a square matrix, the size of HV is the same as the size of V, or the span of HV, the dimension of that is the same as the dimension of the span of V. So this ratio is just half. So that's what it means that when you say everybody gets half the cake, what you're saying is every transmitter receiver pair is able to access 1/2 of the total number of signal dimensions free from interference. So it's as if you had a certain bandwidth and you're able to divide that bandwidth into an arbitrarily large number of competing communications such that each transmitter receiver pair is accessing half of that bandwidth. So in wireless settings, this is important. So now let's see why, how would you construct such a V? So remember in the previous slide we said there would exist such a V which would be invariant to all the undesired channels. So how would you construct such a V? It's very simple. You start with a seed, let's say a random vector. So think of W as a random vector you generated randomly. Let's try to create a space V that would be almost invariant to a linear transformation A. So A could be an undesired channel. So how would you create such a space? Well, here's such a space. Let V be the set of these vectors. So the first vector is W, the second one is AW, and so on. Let's see what would happen to V if we multiplied it by A. So if you multiply V by A, meaning that you multiply each element of V by A, then what you get will almost always be inside V. I mean, so what I mean is multiply W by A, you get AW, but AW is already in V. Multiply AW by A, you get A squared W, but A squared W is also inside V. And that will continue, except for the last term. When you multiply this by A, it will become A to the n plus 1 times W, which is not in V. So that's what I mean, that's almost invariant. It's not exactly invariant. Some part of it will not be, some part of A times V will not be in V, but that's a very small part if n is large. So that's why it's asymptotic, that n has to be large. So this is a space that's invariant.
Syed, one question. I mean, by the Cayley-Hamilton theorem, that also is in the same subspace, right? Because everything, all higher polynomials are linear combinations of these first few.
I'll have to think about that.
Okay. So the Cayley-Hamilton theorem says that if you take the characteristic polynomial and substitute A in it, it is 0. That means higher A to the 100th power is a linear combination of the first few. So it actually is exactly in that space.
Well, but what, let me think. A dimension of A here is.
Oh,
Why? Oh no, so A is not n by n.
Oh, okay. If A is n, yeah. Otherwise, it's a minimal polynomial. Yeah. It depends on the dimension.
It will turn out the A is actually much larger than n.
Okay. Yeah, then it won't work.
Right. So anyway, there's a lot of details I'm hiding, trying to cut corners here to make the explanation shorter. So this is how you would create a space that is invariant to A. Now suppose you want to create a space that is invariant to both A and B. Well then what would that be? It would just be of this form. W, AW, BW, and then all powers of A to the power I, B to the power J, W, and so on up to the nth power. Again, if you multiply this space with A or B, most of the terms you get will be inside the set. So that's what we mean by almost invariant. And now that you can do it with 2, you can do it with any number of them. So that means this is essentially how you create that space V, which can be invariant to any number of TI transformations that you choose. But of course, as I said, the knowledge of channel coefficients is critical here. Now, what I want to point out next is why this scheme is general, how it can solve most, if not all, interference alignment problems. Here's an X network. We saw it earlier with 2 by 2 case. Here you have a 3 by 3. You have 3 transmitters, 3 receivers. Every transmitter has an independent message for each receiver, so there's 9 messages here. Right. So remember, we designed the space V such that it's invariant to all undesired channels. In an interference network, you can identify each channel as desired or undesired. But in an X network, you cannot do that because every channel carries a message, because there is a message between every transmitter and receiver. So what you do here is you say, well, let's look at receiver 1 first. So we will consider only the messages meant for receiver 1. Okay? For these messages, all the channels to receiver 2 and all the channels to receiver 3 are undesired channels. So you will create that space V based on those channels, the undesired channels. Okay? And this V1 is generated according to a certain choice of the initial random vector seed, W, call it W1. Okay, so what that will do is, because it's designed to be invariant to channels to receiver 2 and 3, receiver 2 and 3 will just see V1. Whereas it's not designed to be invariant to receiver 1, so receiver 1 will see a different transformation from each of the transmitters. So you will see H11V1, H12V1, H13V1, all 3 different spaces. Now let's go to all the messages meant for receiver 2. Again, so the undesired channels for these messages would be the channels to receiver 1 and receiver 3. So you design this space V2 to be invariant to those channels. So what will happen is all these V2s will go into the same V2 space at receiver 1. They will go into the same V2 space at receiver 3. But because they're not invariant to their desired receivers channels, receiver 2 will see a different linear transformation each time. Similarly, you will consider the messages for receiver 3, do the same thing, create a space V3, which is invariant to receiver 2 and receiver 1, but not invariant to receiver 3, and that's what you have. Now, all these spaces have roughly the same size. Let's call it V. So how many degrees of freedom are achieved by each receiver? If you look at receiver 1, it's seeing 3 desired Vs and 2 interfering Vs. So it's achieving 3 over 5 DOF. And there are 3 receivers, so the total is 9 over 5 DOF. In fact, that is the information theoretic optimal you can get. So there's no other scheme that can do better than this. And you can also, the same, in fact, exactly the same argument would work the most general X network, where you have M transmitters and you have N receivers. The degrees of freedom would be M times N over M plus N minus 1, using the same argument. And of course, again, the channel knowledge is very important here. You can consider any network, really. The topology you can choose arbitrarily. As long as you have channel knowledge fully, the same scheme will work. In the last, this example, I was quick. This is a cellular network. You have 3 cells. You can have, in fact, any number of cells. You have M users per cell. Again, it could be any number. And we want to see what's the best we can do. So notice in this setting, every channel can be identified as either desired or undesired. So all the red channels are undesired. All the blue channels are desired. So you just need one space V. Let that space V be designed so that it's invariant to all the undesired channels. And the same thing will happen. All interference will align in the same space V, and the desired signals will be distinguishable. So in this case, what would be the DOF achieved per cell? Let's say cell 1. Well, there's 4 V-sized spaces it's seeing. 1 of them is interference. 3 of them are desired. So it's achieving 3/4 DOF. And in general, if you consider arbitrary M and K, the DOF per cell would be M over M plus 1. So notice it does not depend on the number of cells. Of course, it has to be more than 1. And this is also the optimal solution. So again, you can prove an information theoretic outer bound for this, that you cannot do better than this. Of course, if there was no interference, you would have only 1 DOF per cell. So M over M plus 1 gets close to 1 if you have enough users. So it's as if each cell gets almost all the cake. So the solution here is as if there is no interference between the cells. And again, channel knowledge is important. So all these examples are using the same scheme. That's my point, that the same construction that we saw of V's is being used in all these problems. So this is a network coding problem where you have 3 unicasts, and this time inside the network you perform random linear network coding. So you have no control over what happens inside the network. The only thing you can do cleverly is the pre-coding at the sources. It becomes like a wireless channel. And this problem has been studied, again, with the same construction of V's, as I just mentioned. And then, of course, you find out under what conditions would you be able to get 1/2 the cake for each user. Of course, in this case, it also depends on what goes on inside the network. Because, for example, if the network had a min cut of 1, there's no way you can achieve more than 1 DOF for this network. So there are some dependencies that come from the graph that lies inside this network. And therefore, there's a certain set of feasibility conditions. Because what is the condition on this graph that allows that interference alignment solution to work? That has been solved for the 3 unicast setting. Other problems that also use the same solution, for example, the distributed storage repair problem, again uses the same solution. What is the problem? The problem is you have K units of data, and you want to store it in N copies or N storage units. So it's basically an NK code, such that if you lose any of these stored units, as long as you have any K of them surviving, you should be able to recover all the data. That's the constraint in the distributed storage code. It's called an MDS code. So what's the problem here? The problem is, again, I'm describing it at a very high level, not going into details here at all. The problem is that if some of these stored nodes fail, well, first of all, what is stored here? Well, let's say we can store linear combinations of the data in all these nodes. If the code is systematic, then you will have some of them storing exactly what the data was, and the rest of them will be parities or linear combinations. And then the problem is that suppose some of these nodes fail, okay, which means you lose some of these storage nodes. Let's say you lost nodes 1 and 2. Your goal is now to reconstruct nodes 1 and 2. You don't want to construct all the data. The important thing here is you only want to construct what was lost. You want to exactly repair nodes 1 and 2. So you can contact maybe not all the remaining nodes, but whatever number of nodes that you can access. Those nodes you contact, and you download from each of them some information. And the question is, what's the minimum information you need to download from these nodes to be able to reconstruct exactly the nodes that were lost? And it turns out this is exactly the same, even though it doesn't look like it from the description I made of it right now. This is the same problem as the K-user interference channel. So you can think of these linear combinations as being the channels, as we have in the wireless network. So the storage code is the channel. What you download are the beamforming vectors. And what you're trying to do is you're interested only in the information that was lost. That's the desired information. But these linear combinations contain all the other information as well, which was not lost, which is not what you're trying to repair. So that is interference. And you want to minimize the span of the interference in the downloaded information so that you can have more information about the part that you're interested in. So again, don't worry about the details. It also leads you to the information theoretic optimal solution, and it's the same scheme as well. So now I'll switch gears and go on to channel uncertainty, because everything I described so far relies very strongly on channel knowledge. By the way, my clock here says it's 1:46. Would I?
There is no. By the way, because this is the tele seminar, we actually allow much more time, so there is no time pressure. We go on till about 5 with a relaxed discussion after your talk. 5 hour time.
Yeah, I might overshoot by 20 minutes is my guess at this point. Overshoot 4 p.m. Okay, so let's talk about channel uncertainty. What if the channels were not precisely known? Because all the alignment solutions we saw so far depend very strongly on the channel knowledge. So this is an issue that's still, of course, very much an open topic, but there has been a number of results in this area, and I want to summarize some of them. The first model for channel uncertainty that was considered was something called a compound channel. And in this model, what you assume is that for each channel coefficient, the transmitter does not know exactly what its value is, but it knows that it is one of these values which are in a set. So consider a set which has a finitely many values. The transmitter knows that the value of this channel coefficient will be one of these finite values, but it doesn't know exactly which one. So that's a compound setting. And this setting was studied, and it was conjectured that in such a setting, the degrees of freedom must collapse. That is, interference alignment would not be possible if you keep increasing the size of this set from which the channel is drawn. And in fact, turns out that that conjecture is wrong. The degrees of freedom are in fact robust to uncertainty among finitely many values. So you can choose an even large set of values, but as long as it's finite, you will not lose degrees of freedom. And the key is because, remember, the construction of the set of the space V, it's possible to construct a space V that is invariant to an arbitrarily large number of transformations. So when you make the compound setting, you're just increasing the number of transformations. It doesn't hurt. Just as in the K-user interference channel, you get half the total bandwidth, regardless of the number of interferers. The same idea. So that uncertainty model turned out to be not very useful because it tells you that you don't lose anything. So a stricter model of uncertainty is if the channel coefficients values are really unknown, in the sense that the channel coefficient values come from a continuum and you have no idea which value is taken by the channel. So for that, I will present this example to show how is it that you can achieve interference alignment without any knowledge of the channel coefficients. So this is, again, an X channel, the same X channel we saw before. Now, there's an assumption here, which I will justify shortly. What is that assumption? There's a channel variation pattern. So even though the transmitter does not know the channel coefficient values, it knows the channel variation pattern. What is that pattern? The pattern is this. So at receiver A, what we're saying here is the channel coefficients, whatever their value may be, remains the same in channel use 1 and channel use 2. So during the first 2 channel uses, the channel does not change for receiver 1. But the third channel use will be a different channel realization. Whereas for receiver 2, the channel coefficients remain the same in channel use 2 and 3, whereas in channel use 1, there could be a different realization. So how could such a thing happen? Well, there's many ways you can think of it. For example, if receiver 1 was time selective, receiver 2 was frequency selective, then it's possible to create these variation patterns. Another way to do that is if the receivers have these reconfigurable antennas or use antenna switching, which means at any point, this is done, of course, in a deterministic fashion. It doesn't depend on the message or anything. The receiver can switch from antenna 1 to antenna 2, which will change its channel. So it cannot control what the channel will be, but all it can control is that the channel will be different. Okay. So let's see what can we do with the knowledge of channel variation patterns. So the idea is very simple. What the transmitter will do is the following. It will just use repetition. It will just repeat the information, and it will repeat it over those channel instances where the desired channel is different, but the undesired channel is the same. So what does that mean? So consider the symbols A1, A2. These 2 symbols are meant for receiver A. So let's try to find 2 channel uses where the desired receiver's channel changes, but the undesired receiver's channel remains the same. So these are channel uses 2 and 3. This is channel use 2, channel use 3. Over these 2 channel uses, receiver A's channel changes, but receiver B's channel remains the same. So what you do is just repeat A1 and A2 over these channel uses. That's what this precoding vector means. You're not sending A1 over the first channel use, but you send A1 and you repeat it again over channel uses 2 and 3. Same thing with A2. So what does that do for the receiver? At the desired receiver, because the channel changes, you will see two different linear combinations of A1 and A2. But at the interfering receiver, because the channel has remained the same, you will see the same linear combination twice. That's where the alignment is happening. So you can see that there is an alignment because the undesired variables are appearing twice in the same way. Now let's consider variables B1 and B2. These are desired for receiver 2. We need to find two channel uses where the desired channel changes, but the undesired channel remains the same. These are channel uses 1 and 2. So you would repeat B1 over channel uses 1 and 2. And what that would do is, over the undesired receiver, they would give you the same linear combination twice. And at the desired receiver, you would see two different linear combinations because the channel changed. So now these are the three equations in 4 variables that each receiver sees. Can they all recover what they want? Well, let's look at receiver 1. The undesired variables being B1 and B2 appear twice in the same way. You can just cancel it. First equation subtract from the second, that gets rid of B1 and B2. And what you're left with is 2 equations in 2 variables that you care about, from which you can solve A1 and A2. Similarly, at receiver B, the A1 and A2 that are interference are aligned, so you can cancel that, and you're left with 2 equations, 2 variables from which you can solve B1 and B2. So this is a blind interference alignment scheme because notice that the transmitter's choice of pre-coding vectors does not depend on the channels H1, H2, H3, H4. So the transmitter does not know the values of these channel coefficients. All it knows is the channel variation pattern. And perhaps more surprisingly, the DOF that you achieve here is 4 over 3, which was, if you remember, that was also the degrees of freedom value when you had perfect channel knowledge. So you did not lose anything from not knowing the channel. This slide is not something I'm planning to explain, but this is just to show that these things generalize. You can go to an M transmitter, N receiver, X network. And of course, again, you would have to carefully plan how the antenna switching happens. For example, if you had 3 transmitters, 3 receivers, this would be how you would switch antennas. And this pattern kind of reminds me of wavelet transforms, but it's something I have not really thought about too much. But what happens is that you get the same DOF, Mn over M plus N minus 1, as you would with perfect CSID, so again, without knowledge of channel coefficients. But of course, the key here, or the trick that we played, was that we exploited these channel correlation patterns. So what if we tie our hands even more and say that, well, not only does the transmitter not know the channel coefficient values, but the coherence patterns are identical. Every receiver has the same coherence pattern, and there's no way to manipulate them. You don't have reconfigurable antennas. You cannot do any switching. There's nothing to play with. Can you still achieve interference alignment? That's the question. Okay, so to answer this question, and here what we will exploit is the locally connected nature of wireless networks. And I will explain this with this simple example. And this is where I'm heading into index coding, so it's coming up shortly. This problem, as I will argue as a heads up, is actually an index coding problem. Okay, so you have, what is this problem? In this problem, you have 4 cells. Each cell has a base station in the center, so here's the base station transmitter A, transmitter B, C, and D. Then these are the users. I'm interested only in the users that are located near the boundaries, because these are the users that can hear 2 cells. Right? So for example, users A1 and B1, these receivers can hear both transmitter A and transmitter B, whereas receiver B2, D2 can hear B and D, and so on. What do the transmitters know? The transmitters know only the connectivity. The transmitter knows that A2 and C2 can hear transmitter A. And for example, C1, D1 cannot hear, but it does not know the channel values. And there are identical coherence patterns. There's no reconfigurable antennas, and so on. So what is the degrees of freedom of this setting? So first, let's do what would be a very simple solution. A natural thing you could do is, because there's only interference between adjacent cells, you make sure that adjacent cells get different resources. So for example, you could divide the spectrum into 2 and give half of it to cells A and D, the other half to B and C. In that case, every cell would act as 1/2 of the spectrum. The total DOF would be 2 per cell. But is this optimal? Is a simple solution optimal? Well, as we'll show, the actual answer is 8 over 3, and this is the best you can do. Of course, it's bigger than 2, and it will use interference alignment. So how does that work? It's the same picture as before. I'm just drawing it in a little less fancy way. These are the transmitters A, B, and receivers at these edges. Remember, receiver A1 can hear both A and B, and so on. So what happens here? Well, transmitter A, the base station A, will send symbol A1 during the first channel use, A2 during the second channel use, and stay quiet during the third channel use. Transmitter C will do C10, C2. Those are the 3 transmissions. Transmitter B sends B1 every time. It repeats B1, but it sends B2 only during the second channel use, and transmitter D repeats D1 every time, but sends D2 only during the fourth channel use, or third channel use. So let's see why that works. So consider receivers A1, B1. Notice that the transmitters have no way of distinguishing these 2 receivers because they have the same connectivity. These 2 receivers can hear base stations A and B. And none of the transmitters knows the channel coefficient. So really they have no way of distinguishing these 2 receivers. So both these receivers will be able to decode A1 and B1. Let's see what happens. Receivers A1 and B1, during the first channel use, they will see a linear combination of A1 and B1. Second channel use, they will see a linear combination of A2 and B1 plus B2. And third channel use, they will see just B1. So can they recover A1 and B1? Well, of course, from the third channel use, they recover B1, and from there, you can subtract it out from the first one, you get A1 as well. So both of these can decode A1 and B1. Now consider the receivers A2 and C2. If you look at the 3 linear combinations, the first linear combination is a combination of A1 and C1. Second one is just A2. Nothing is transmitted here. Third one is just C2. So of course, they can recover A2 and C2. Go to C1 and D1. The first channel use is a linear combination of C1 and D1. Next one is just D1, and the third one is a combination of C2 and D1 plus D2. And again, from here you can recover C1 and D1 because D1 is from here. After that, after you have that, you can recover C1 as well. Remember, the receivers know the channels, right? The transmitters are the only ones who don't know the channels. Now, the most interesting case is the last one, B2, D2. What happens here? First channel use, you see B1, D1, linear combination of that. Second channel use, you see a combination of D1 and B1 plus B2. Third channel use is B1 and D1 plus D2. And from here, you want to recover B2 and D2. Well, so how would you recover B2? Well, from the second equation, subtract the first one, you will recover B2. From the third equation, subtract the first one, you'll recover D2. So you can recover both B2 and D2 as well. And this is an interference alignment solution because notice that every receiver is seeing 4 variables and 3 equations. And every receiver is seeing 3 equations and 4 variables, from which it wants to recover 2 variables. So of course, the remaining 2 variables have to align in 1 dimension. That's what's happening at each of the receivers. So another interesting side remark here is that in this problem also, even if you had perfect channel knowledge, you could not have done better. 8/3 would be the capacity if you think of it as a network coding problem, or the degrees of freedom if you think of it as a wireless network. So now let's see why this is an index coding problem. So I will do some transformations of the same thing. So this is the original network. I will first represent it as a partially connected X network. And what that means is it's the same picture over here. What I've done is, remember, as I said, receivers A1 and B1 are indistinguishable. So I've replaced them with one receiver. I'm calling it AB. Okay. Similarly, A2, C2, I'm calling them one receiver, CA. This receiver should be able to decode both A2 and C2. So I have transformed it into a 4-transmitter, 4-receiver network. This is the connectivity. So for example, this receiver, A2, C2, this is the receiver CA, should be able to hear A and C. So this is the CA receiver. It should be able to hear A and C. This is the wireless network setting. Okay. So that's the connectivity pattern. This is an X network. There are 8 messages, just as there were in the original network. For every transmitter, there's a message to each connected receiver. Now, the next thing I'll do is I will make the network fully connected. But to do that, if I just make it fully connected right now, I will add interference. So I will protect the receivers from interference by first providing them with a Genie information that will allow them to clear out the interference. So at receiver 1, for example, I will provide them all the information which will allow them to reconstruct and subtract out the new channels that I add. I will add these 2 channels. My goal, remember, is to make it fully connected. When I add these 2 channels, I'm adding interference from transmitters B and D to receiver CA. But I've also provided him the side information that will allow him to completely subtract out these signals. So information theoretically, this network is equivalent to the previous one. Nothing has changed. Same thing with the second receiver. I will make it fully connected, but the interference that I'm introducing I will also provide that as an antidote. So it can subtract it out, but there's no harm and no gain either from having this fully connected network. Same thing in all receivers. So I've made everything fully connected, and I have the side information at each receiver. Now the next thing I will do is I will make this channel rank 1. Why can I do that? Because remember, the transmitters have no knowledge of the channel coefficients. So the receivers are, the network is now fully connected, and the receivers are statistically equivalent. And in information theory, there's a property we use, which is same marginals property, which says basically that the capacity depends only on the marginal distribution of each user's channel. So in this case, without loss of generality, you can assume every receiver sees the same channel coefficient. Every receiver sees the same channels. And of course, these channels are not known to the transmitter. So once you say everyone sees the same channels, the overall channel matrix becomes rank 1. And at this point, the next step we'll do is allow full cooperation between the transmitters. This is the only step that can actually increase the capacity. Everything else we've done so far is the equivalent. There's no change. But as we will see, that this increase will almost never happen, extremely rare. Okay. So next step, we allow all transmitters to cooperate, which makes this a broadcast channel. There's only one transmitter. Remember, it was a rank 1 channel, so you can model it as a transmitter with only one antenna. And once you have that, that is exactly the index coding problem. This is another representation of the same problem, and this is what one would recognize as an index coding problem. And I will go a little bit more into the index coding problem to explain what that is. So this is the index coding problem as it was introduced in 1998 by Burke and Cole. And in fact, it's the first example that I know of interference alignment being applied anywhere. So this is the 98 paper. So what is index coding? You have a transmitter. This is the example from Burke and Cole's paper. The transmitter has 5 messages, A, B, C, D, and E. There are 5 receivers. Receiver 1 wants A, receiver 2 wants B, and so on. Now, each receiver has prior knowledge of some of the other messages. For example, receiver A already knows B and E, and receiver B already knows A and E, and so on. So it's a broadcast channel with cognitive receivers. That's what I meant. Another representation of the same thing, as I said, these two are equivalent representations, is this form, and this is the one I will use more commonly for index coding problems. Here you see the 5 messages, A, B, C, D, and E. These are the transmitters. On the right-hand side, you have the receivers that want A, B, C, D, and E. And the important thing here is every channel that you see in this network has capacity infinity, except for one channel at the top. This finite capacity link is the only one that has finite capacity. Everything else has infinite capacity. So what does that mean? If you have an infinite capacity link from this transmitter B to receiver A, it means it can send its message B entirely, because that's all it knows, to receiver A. So that's how receiver A is cognitive. It has B as side information. So this antidote link is modeling that side information. And this finite capacity link is the only place because there's a one-dimensional transmission from here, which would be the same thing as a unit capacity link over here. So that's the index coding problem. In this problem, let's see what the solution is. This is the solution presented by Burke and Cole, and why it's an interference alignment solution. So let's look at receiver A, for example. So what happens here is over this the only link that has finite capacity. Here you will use this link twice. And what you will send is over the first channel use, you're sending A plus B plus E. Over the second channel use, you're sending B plus C plus D. Okay, so that's what's being transmitted. Now at receiver A, the receiver A already has B and E as antidotes. It knows what B is and E is, right? So it can subtract that out from the equation. What it's left with is 2 equations in 3 variables. There are 2 equations, and there are still 3 variables, A, C, and D. But notice that C and D, which are the undesired variables, actually occupy the same space. Right? They span only a one-dimensional space. So that's where alignment happens. So because undesired variables align in one dimension, you're able to recover A from the other dimension. In fact, Burke and Cole even call this example a miracle. So they were very surprised that this happened. And it is, in fact, interference alignment. So let's go back to our problem, the toy example that we had, the 4-cell setting. What we said, we started here and we ended up here, and we said these 2 problems are the same, except there was one step at which we allowed transmitter cooperation where things could get better. I hope this example is clear. You have 4 transmitters. These are the messages, WA1, WA2. Those are the 2 messages. What is WA1 intended for? WA1 is intended for this receiver. He wants to decode WA1. And similarly, A2 is intended for this receiver. He wants to decode it. And these are infinite capacity links, which means this receiver, for example, knows WA1, WA2. He also knows WC1, WC2. So anytime you have an antidote link, all the information is sent from that transmitter over that antidote link. So that's the index coding problem. So what will be the solution? So in fact, what I'm saying is these problems are equivalent not only in that their final capacity will be the same. In fact, their solution will be the same too. So remember, this problem we solved by saying that transmitter A will send this and transmitter B will send this and so on. That was the solution. What will be the solution in the index coding problem? It will be the same thing, XA plus XB plus XC plus XD. That's what you will send. And each receiver, of course, will remove the part that he has antidotes for and be left with the part that he does not have antidotes for. So what will happen is the same thing as we saw before. This network, the wireless network, has 8/3 degrees of freedom. This index coding problem has capacity 8/3. And you can make that general. So here I want to point out the general relationship, even though I'm doing this with a specific example again. But this is another example for you have 5 cells, and this is the connectivity pattern. The transmitters are in the middle. Every receiver in that circle is able to hear the transmitter. So for example, the black squares are transmitters, white squares are receivers. So let's look at receiver 1. So this is receiver 1. Which transmitters can receiver 1 hear? Well, he happens to be inside the circle for transmitters 1, 2, and 5. So you will see in this connectivity pattern also that receiver 1 can hear transmitters 1, 2, and 5. So this is just a less fancy representation of the same problem. So this is the X network. And this is the corresponding index coding problem on the right-hand side. What's the relationship between the two? If you look at the graph of the index coding problem, those red antidote links are the complement of the graph of the wireless problem. So wherever you see a connection here, there would not be a connection here, and vice versa. So wherever you see an antidote, there would not be a connection here. So the 2 graphs are complements of each other. So what's the general relationship? If you take a wireless network, and these are not arbitrary connectivity, but what I'm saying here is true even with arbitrary connectivity. So take any wireless network with arbitrary connectivity, no CSIT. The transmitter does not know the channel coefficient values, except that it knows it's non-zero. Okay? Which ones are 0 and which ones are non-zero. That's what I mean by connectivity information. So take such a wireless network, and for that network, consider the corresponding index coding problem, where the index coding problem will have the complementary graph. And what you will find is that the degrees of freedom of the wireless network will in general be less than or equal to the capacity of the index coding problem, because there was a step at which we allowed cooperation between transmitters. Things can become better. But the relationship is even stronger. I can say something stronger. I can say that the two will be the same anytime that the linear vector space solution is optimal. In all the examples that I showed you, the optimal solution was a linear vector space solution. Remember, the transmitter was sending a certain set of vectors. The receiver was looking at the alignment of these vectors. It was all linear operation, right? So whenever a linear vector space solution is optimal, the degrees of freedom of the wireless network with arbitrary connectivity will be exactly the same as the corresponding capacity of the index coding problem. Of course, when linear solutions are not optimal, the index coding problem can have a higher capacity. And to give you an idea, in fact, for the index coding problem, for the multiple unicast index coding problem, which is what all of these are all multiple unicasts, it was not known that linear codes are not enough to achieve capacity. So every example that you have, linear codes are enough to achieve capacity. So in fact, it was shown that linear codes are not enough for index coding if it's not a unicast problem, but a multicast problem or a group cast problem. And in fact, one of the recent results we've obtained is also to show that for the unicast index coding problem, also linear codes are not always enough. So this situation will not always happen, but it happens most of the time. It's very hard to find examples where it does not happen. So For example, in this case, this is the last example I will do. The wireless network we started with will turn out to have 5/2 degrees of freedom. Of course, this network has 5/2 degrees of freedom because it is the same network as the previous. I'm just not drawing the circle. That's the only difference. So these two problems, of course, are the same. And the index coding problem will have an exact capacity of 5/2 because it corresponds to this network, and linear solutions end up being optimal. So to give you an idea of how complicated can these solutions be, I will show you the solution for this network. So this is the index coding problem. The sum capacity here is 2.5 or 15/6. Notice that there are 15 messages here because there's a message from each transmitter to each receiver where no antidote link is present. So from this transmitter to this receiver, there will be one message. That is the message 5. Well, this is shorthand notation, I should explain. When I say W4, 5, 6, what I mean is W4, W5, and W6. There are 3 messages. Okay. So there are 15 messages that you need to send over this, and you can, the optimal solution is this. You use the channel 6 times to send those 15 messages or 15 symbols, so the sum capacity becomes 15/6 or 2.5. And these are the 6 transmissions that will occur over this bottleneck link. And this, I will not go into how this solution was obtained, but it's obtained pretty much using the vector linear alignment solutions, vector linear alignment arguments. I will just explain how the solution, or just give you some brief look at why it works for receiver, let's say this receiver, which wants 9, 11, and 13. So this receiver, let me go back. This receiver already knows as antidotes messages 1, 2, 3, and messages 4, 5, 6. Right? They're available to this receiver as antidotes. So 1, 2, 3, 4, 5, 6 are all available as antidotes. So from the received signals, notice that every receiver sees the same received signals in the index coding problem. Because whatever is being transmitted here is exactly what's being seen by all the receivers. So he can remove 1, 2, 3, 4, 5, 6. So all these blue things he can remove. What's left is the desired signals and the interference. So there are 6 interfering symbols and 3 desired symbols, a total of 9 symbols, but you're in a 6-dimensional space, so there are only 6 transmissions. But as it turns out, the 6 interfering symbols only span a 3-dimensional space. So if you look at the beamforming directions for each of them, they will span only a 3-dimensional space. So really, it's as if there are only 3 interfering symbols. And so therefore, you have 6 equations. You can separate the 3 interfering symbols from the 3 desired symbols and decode everything. Okay, so now the last bit I have is very trivial stuff. I just want to take advantage of this equivalence between the cellular network and an index coding problem to show you some nice simple solutions that emerge for the cellular network setting. So here I have a linear array model of cellular networks. So you can think of each of these squares as being a cell. In the middle is the base station, that's the transmitter. And I'm only considering users near the cell edge. So I have 2 users in each cell, 1 at each of the cell edges. The users near the cell edge can hear both base stations that they're close to. That's the model. Okay, that's the connectivity model. They cannot hear anything else. Each receiver can only hear the 2 base stations that are close to it. So because interference happens only between adjacent cells, the simple solution here would have been to just divide, let's like the coloring problem. You don't want 2 adjacent cells to have the same color. So you would use 2 colors to color everything. So basically every cell is accessing 1/2 of the bandwidth. So the simple solution would be 1/2 DOF per cell. What would be the optimal solution? This is the interference alignment solution too, even though it's a little bit simple. The optimal solution is this one, where you turn off, these gray cells are turned off, meaning the transmitter is not transmitting. The red arrows indicate which user is being served. So in this cell, in the second cell, you're serving the user on the left. And why can you serve this user? Because the interfering transmitter is off, right? He sees no interference. He can totally see his own signal without any interference. In fact, it's an orthogonal solution in some sense. In this next cell, you're serving the user on the right. Again, there's no interference because the next cell is turned off. And you can continue this pattern. So what would be the degrees of freedom you would achieve? You would achieve 2/3 per cell, and you can prove the information theoretically this is the optimal solution. And of course, you can also present this as an index coding problem, in which case this would be the capacity, 2/3 per user or per transmitter. Now let's make a square array instead of a linear array. So again, it's the same model. These are the cells in each square. The center is the base station. There are users at the boundary. Each user at the boundary can hear the 2 base stations that are close to it. The simple solution would be, again, this orthogonal solution, which is 1/2 DOF per cell, because no 2 adjacent cells have the same frequency allocation in this solution. But what's the optimal solution? The optimal solution is this one. It's the interference alignment solution again, where you turn off a cell. So for example, this cell is turned off, and then you're serving all the users that are adjacent to this cell. Okay? And if you look at the solution carefully, there is no interference in this frequency allocation. So, and the DOF here are 3/4 per cell. So you go from 1/2 to 3/4. It's a bigger improvement than in the linear array. Now, what if we went to hexagonal cells? This is the last example. Again, because you have interference only between adjacent cells, the simple solution would be a coloring solution where no 2 adjacent cells have the same color. You would need 3 colors. So this would be DOF 1/3 per cell. This is the 1/3 frequency reuse pattern that's used in cellular systems. But what's the interference alignment solution? Again, it's this is the interference alignment solution, where you sacrifice a cell and you serve all the users on the boundary of that cell. What's the DOF that you achieve here? It's 6/7. So you went from 1/3 to 6/7. Actually, that's a pretty big improvement. So these are simple patterns, but these are all cellular frequency planning problems, but you can also think of them as index coding problems, and the solutions would always be the same. That is pretty much at the end of my talk. Thank you.
Thank you very much, Syed.